The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, everyone. Welcome to today's AI for Manufacturing webinar. My name is Li Hui Wang. I work for KTH, Royal Institute of Technology, located in Stockholm, Sweden. I'm very honored today to moderate this webinar. The topic of today's keynote is an integrated modeling and simulation language for MNS-based system engineering. We are fortunate to have Professor Lin Zhang of Beihang University with us today to talk about this topic. Let me firstly introduce Professor Zhang properly. Professor Zhang received the BS degree in 1986 from the Department of Computer and System Science at Nankai University, China. He received a master's degree and a PhD degree in 1998, 1989, and 1992, respectively, from the Department of Automation at Tsinghua University, China. From 2002 to 2005, he worked at the U.S. Naval Postgraduate School as a senior research associate of the U.S. National Research Council. He served as the president of a Society for Modeling and Simulation International, in short, SCS, the executive vice president of China Simulation Federation, CSF, and the president of Asian Simulation Federation, Asian SIM. He is a fellow of SCS, Asian SIM, and CSF. He served as the director of Engineering Research Center of Complex Product Advanced Manufacturing Systems, Ministry of Education of China, editor-in-chief and associate editors of 8 peer-reviewed international journals. He authored and co-authored more than 300 papers, 20 books, and chapters. His research interests include modeling and simulation of complex systems, cloud manufacturing and simulation, model engineering, model-based systems engineering, cyber-physical systems, M&S for manufacturing systems, etc. Ladies and gentlemen, without further ado, please join me in welcoming Professor Lin Zhang to the virtual podium. Professor Zhang, the floor is yours.
Thank you, Professor Wang's introduction. It's really a great honor to have the opportunity to report my group's recent works on the integrated modular simulated language for MS-based system engineering on the platform. So my presentation will have 3 parts. The next one, please. First, I will briefly introduce the MS-based systems engineering, and then introduce the X language and the corresponding software tools we developed, and then give a conclusion and the future works. Generally, systems engineering is used for development of complex systems. So let me quickly review the features of complex systems. With the development of science and technology, our world we build become more and more complex, such as the city we are living in, the traffic in the city, large manufacturing companies, military systems, and so on. In fact, it's not easy to give a definition about complex systems, but generally they have some important characteristics, such as strong nonlinearities, uncertainties, and complex relationships among the elements, and the elements and their associated relationships will continue to evolve, resulting in an unpredictable phenomenon that excuse me, that never manifested in the subsystem. Next one, please. Okay. The development process of complex products is a very typical complex system. It's a kind of system of systems. For a complex product, such as automobiles, airplanes, ships, and engines, its structure is very complex, and it generally includes dozens of or even hundreds of disciplines, such as the structure, the materials, pneumatics, fluids, electronics, electromagnetics, and so on. The structure of a product can be divided into different levels, such as the system level, subsystem level, equipment level, component level, and part level. And the life cycle of a product is generally long. The phases include demand, analysis, design, manufacturing, experimental testing, sales, maintenance, and even destruction. Every phase may last a long time, and the system keeps evolving within the whole life cycle. The development of such complex products often requires a large number of units and departments to work together. Next one, please. The development of the complex products required assistance of systems engineering, methodology, and the tools, especially for top-down design of a new product. This figure shows a traditional systems engineering method. In the system design phase, the left shoulder of the V model, the information exchange between various departments mainly relies on traditional documentations Most of the documentations are unstructured, written by human, is non-standard, and even ambiguous. It means sometimes the same terminology has different meanings in different domains, and different people from different departments may give different names for same things. So this results in the difficulty of communication with the traditional documentations. And in the system integration stage, the right shoulder of the V model is mainly the assembly of the physical systems, making it very expensive and time-consuming to repeat trial and error. Next one, please. Next page, please. Now, the traditional systems engineering, also named as the TSE, the text-based systems engineering or document-based system engineering. So activities in TSE produce lots of documents, mainly written with natural language, including some unstructured data, such as tables or figures. In the development process, various departments have accumulated a huge number of documents written by different people in different formats with different tools. It's a disaster for engineers. There are some disadvantages summarized as follows. First, the integrity of information. Excuse me. It's difficult to evaluate because they are scattered across various and numerous documents. Second, it's difficult to build relationships, correlations between documents, because the documents are isolated and saved in different files. The third, it's difficult to maintain consistency among various documents, especially for documents changes. Due to the large number of documents, when make one change in a document, it's difficult to guarantee that all related contents will be changed accordingly. Fourth, as a result, it's difficult to track back to find a valuable clue if some problems happened in the final product. The fifth, the vague meaning I just mentioned before. So we have some terms may have different meaning and different things may have the same name. Finally, it's difficult to describe complex activities with normal language, with natural language, because activities are dynamic and interactive. For text-based documents, it's difficult to describe spatial and temporal logical relationships of complex activities clearly. Next one, please. Now, it's the model-based system engineering, MBSE. So MBSE is an important approach to deal with the challenges faced by traditional systems engineering. The core idea is to support the various stages of systems full life cycle through a unified, formal, and standardized model. The exchange of information between engineers in different departments changes from the traditional text-based model to model-based mode. Based on the unified model, everyone used the same standard to work and communicate, which can overcome the shortcomings of the traditional systems engineering and greatly improve the efficiency of collaboration and the quality of developed systems. The INCORS, the International Systems Engineering Society, gave the definition of MBSE as follows. Model-based systems engineering is the formalized application of modeling to support system requirements, design, analysis, verification, and validation activities, beginning in the conceptual design phase and continuing throughout development and the later lifecycle phases. Next one, please. Currently, the system modeling language is short for SysML, is the most frequently used modeling language for the purpose for MBSE. It was developed by INCORS and OMG organization based on Unified Modeling Language. The UML is for software engineering. SysML adopts the main idea and methodology of UML. It's also a diagram-based modeling language. It took many elements from UML and added some new elements to support system development. Next one. These are examples. This system diagram. The left picture, the left is the diagram of SysML. So some are the same as UML, some changed. There are two diagrams are new. The right picture is an example of SysML model. Next one, please. In traditional systems engineering, different departments communicate with documentation, such as mentioned before. They transfer documents from one department to another one and discuss based on natural language in the documents. So in MBSE, it's different. The transfer of documentation becomes the evolution of models. So people of different departments discuss problems with models, especially when some problems occurs. It's easier to find the reason with models than with documents. This change is a very big change for engineers involved in development activities. So sometimes MBSE is considered as a revolution of systems engineering. But so far, for the V model, only half of the problems have been solved. In the right shoulder of the model, if system integration method is still based on physical prototype, the efficiency will be still very low. It's to be very time-consuming and expensive, and the limitations are still very big. Next one. To completely change the traditional development mode, it's also necessary to use simulation technology to turn the integration of physical systems into the integration of digital models to further shorten the development lifespan, reduce costs. Click, please. Yes. And improve efficiency, and even to achieve a successful manufacturing at the first time. This is actually a modeling and system and simulation-based system engineering. So in simulation society, we prefer to call the MBSE as MSBSE. Next one, please. The problems and the challenges. If you want to establish a system model that reflects the architecture and the physical features to perform simulation of the whole system, the SysML, the language, is not enough to support the idea, the methodology of MSBSE. So other languages have to be used to collaborate with a SysML modeling tools. The conversion between SysML model and other kind of simulation model, for example, the Modelica or Simulink, has to be done. And the interface standards, such as the FMI, have to be used to realize the integration of different software tools. Next one. How to organically combine system design with system simulation to achieve cross-level model transformation and support efficient design, as it's an important research topic. At present, efforts from academy and industry mainly focus on two directions. The first one is to do the conversion between different type of models, such as SysML to Simulink conversion, SysML to Modelic conversion. Some transformation language have also been developed to specify the transformation between models. This is the first research direction. The second one is to do the integration of different software tools to develop better interface between system level modeling software and the physical level simulation software. But in fact, for two different models developed by different languages, it's impossible to transfer one to another 100%. Missing some information is inevitable. The mutual operations are unavoidable during the process of model conversion or software integration. So there are a lot of difficult work have to be done by human manually. The next one, please. Any parameter so we don't follow, but what we are going to do, so we developed a new language. We don't follow the conventional idea. We go another way. We try to solve the problem fundamentally to get the root. So we developed a new language that we called it X language. It can build the high-level architecture model and low-level physical model as one model. and the model can be simulated directly. So to avoid the conversion of models and the integration of software tools. So this language can deeply integrate the ideas and descriptions specifications of existing modeling languages and specifications. It can realize the unified description of system model and multiple domain physical models. So it can fully support MSBSE. Or in other words, it can completely embody the value of MBSE. Next one, please. DEVS is discrete event system specification. So it's posed by Professor Bernie Ziegler. It follows the Weimar's system framework to provide a computational base for modeling and simulation. So DEVS is a modular and hierarchical formalism for modeling and analyzing general systems. So X language draws on the theory of DEVS to realize the joint sewing of hybrid system model containing both continuous states and discrete event states. Next, please. The DEVS describes the structure of the system and behaviors through interaction of atomic and couple models. So it can be used as a computing framework to develop the new language. Next one. So the next part, I'm going to introduce the X language and the software. One more click, please. As mentioned above, the X language draws on ideas from different modeling languages and specifications, including the SysML, Modelica, and DEVS, and agent modeling languages and other kind of language specifications. This is the right is the structure of X language. At the system level, graphs like SysML describe the system level modeling, including the requirement structure, etc. At the model entity level, a description for couple models is given based on DEVS rules. Follow the object-oriented design principle. The X language describes the functions and performances in the form of variables and equations, and support continuous time modeling, discrete event modeling, agent modeling, and hybrid system modeling. Next one, please. So how to realize the hybrid modeling? We should have a theoretical foundation, and based on the method to design the X language syntax and the semantics. So based on the DEVS, we developed XDEVS. It's extension of DEVS to support the syntax design for 3 types of hybrid system modeling and simulation. The type 1 is systems whose states are primarily shown as continuous trajectories, but the trajectories are divided by discrete events at certain time points. The type 2 systems whose states are primarily driven by events, but the state change continually in certain time intervals. The type 3 is the combination of the type 1 and the type 2. So it's a hybrid components with dynamic interactions. Next one, please. So XTAPs is composed of couple, atomic, and state. So the states exist as an independent element in XTAPs and have two types of states to model discrete and continuous states. So we introduced continuous states in XTAPs. Well, that's the structure of the continuous and the couple, the states, and the state statement is shown here. And also we have published a paper as give details of the theory. So for now, I'm going to go to the details. So next, please. So the classes in X language is the basic element. The classes for different type of objects are designed to support, to describe different kind of characteristics of a complex systems. The class is consisted of basic parts, including definition, connection, equation, state, and action. To enhance the ability to describe the intelligence behavior, the agent class is added to X language. And reinforcement learning is integrated into the agent class to support modeling of intelligent learning behavior. So X language can build the model of intelligent manufacturing systems. The next one, please. A class is often a combination of multiple parts, including the requirement, definition, connection, state machine, equation, and activity. So the different parts of class are corresponding to different diagrams. That is the requirement diagram, definition diagram, connection diagram, equation, and statement activity diagrams. So it's a very obviously characteristic of X language. So we give two forms of descriptions for one model. One is graph, the other one is textual code. Next one, please. So the diagram model, the graph model, is easy to be understood by human beings. So it's used for engineers for discussion and communication. And the text model can be understood by computers. So with the text model, the text form model, there are a lot of advantages. And it can do a lot of things. The text model can be used as a knowledge mining and can build the correlation between the different text, between the different models. You can use the AI technology with the text form, the code, So it's very easier to analyze the characteristics of models than with the graphical models. So the different parts of class are corresponding to different diagrams. This is the corresponding correlations in the right graph, the right picture. And the diagrams and the textual code can be mutually converted automatically. So we have developed tools to automatically transfer the one kind of model, the diagram model, to another kind, the texture model. Next one, please. To support the X language to be used in MPSE, so we have developed a software tools. We called it XLab, because the X language is developed in our lab, so we called it the XLab. The core parts of the software include a compiler and a simulator. The compiler is an objected excuse me, object-oriented architecture. X language does include features of both traditional programming languages and equation-based modeling languages. So the compiling process of X language is different from either traditional programming language or equation-based modeling languages. And the compiling the X language compiler, we used a new kind of technical route. Next one, please. The compiling process is divided into three parts. The first one is the pre-processing stage, and then the middle processing stage, and the post-processing stage. The main difference is the later two parts. And the compiler can translate or compile the X language textual code into C++ programming language code. Next one. And based on the C++ code, we can do the simulation of the model with the simulator or simulation engine. So this is the structure of the simulator. The hierarchy of the simulator is corresponding to the hierarchy of X language models. So the simulator can run the model based on the C++ code compiled, translated by the compiler. Next one, please. So there is the interface of XLab modeling environment. And actually, this software is online. So you have a link in the bottom of the slides. The next one, please. Okay, so we have built a model library, because model library is very important for modeling tools for engineers. Currently, XLab model library include more than 6,000 basic models of multiple disciplines, such as the mechanics, electronics, control, hydraulics, and so on. In the future, and actually we are still working on expanding the professional model library. And also are working on to further improve the professionalism of the XLab software. Next one. Oh, this is the tool set of the XLab. So it includes modeling environment supporting graphical and textual modeling, a synthetic checker for verification of models, a compiler that can compile the X language codes into C++ code, a simulator to do the simulation of the whole model, and a model library. Next one, please. Now, based on the X language and the toolset, we proposed a methodology for modeling simulation-based system engineering. So it gives the whole process of how to do the modeling and how to do the simulation based on the X language to finish the design and validation and verification of the system. By using X language, the methodology we developed, we called it XSEM. It means X language-based systems engineering methodology. It bridges the gap between system design and validation. And we can do validation by integrated simulation with one model. The transformation between SysML and Modelic or MATLAB Simulink are not needed anymore. Next one. Excuse me. The XSEM follows the system design philosophy known as RFLP. It's requirements, function, logical, architecture, physical, architecture, physical architecture. So it's RFLP. So we give the way of how to realize the different activities with X languages. So how to do the requirement analysis, how to do functional analysis, and the system conceptual design, unit design, and integrated validation. So the picture looks a little bit complicated. The next one, please. The process of modeling simulation with X language is shown in this feature. The input file can be code or graphics. The code format can be directly sent to the compiler, and the graphics need to be converted into codes and then processed by the compiler. After the compiler receives the modeling codes, it translates the X language codes to C++ codes. The generated C++ code will be executed based on the simulator. Next one. This is the structure of a system model built with X language. It includes 4 parts: the high-level, conceptual, and structural model, the unified multi-domain physical performance model, and the detailed descriptions and interface with other models. Because sometimes enterprises or organizations have built many models with other kind of languages. So the XLab software tools also have the ability to integrate to integrate with the other kind of models built with other kind of software tools. Next one, please. There are some examples. It's a circuit model, circuit system, and modeled by XLab. In the middle is the model of X language. The upper one is the graph model. The lower one is the text code. They are the same. They can translate it automatically with the tools. And here is the simulation results. Next one. This is the water tank model. It's often used for control to demonstrate control theories. So because there is the controller can be taken as an agent. So we built this model with X language to build the agent part. Another example, next slide. Yeah. This is the X language model. The left is the graph, the right is the text code. Next slide is the simulation result. Next one, please. Yeah, this is the simulation result. So the model, when the model is built, you don't have to do anything manually. The simulation is automatic. So that's the main difference between this kind of methodology and the traditional MBSE. Next one, please. Yeah, this another example is aircraft attitude control model. Next one. This is the model built with XLab. The left is the graph model, right. The right is the text model and the simulation result. Next one, please. This another example. The modeling simulation of a fuel cell vehicle. Next one. Yeah, here is a little bit complicated example. We do the comparison of the two kinds of methodologies. First one, we use the traditional method for the design and simulation of aircraft taking off. The process of aircraft taking off. The current method is to analyze the requirements and the interaction logic of subsystems with SysML and get a system level model with SysML diagrams. To analyze the flight environment and flight dynamics properties with MATLAB and Simulink. FMU is used to connect the SysML model and the MATLAB model to conduct the whole system simulation. Next one, please. This is the SysML model. It's the system architecture. And the next one is MATLAB and Simulink model. The next one, please. Yeah, this is the Simulink model. Use MATLAB to build the dynamic model of the aircraft, the system. So with the SysML parameter diagrams, the data interaction between the system level model and the physical level model. So that is realized with the FMU. It's a kind of interface standard between different softwares. So many system simulation software can support this kind of standard. Next one, please. Now, we do this. We'll do the same thing with the X language and the X lab. So we don't have to build two models, the sys model, this and the dynamic model with two different softwares. We just built one model, and with one compiler and one simulator to get a final simulation result automatically. Next one, please. With the XLab, so we can build a top-level description with a couple class and establish a system-wide model and directly realize data interaction through the part of X language. With the discrete class to build the behavior logic between each subsystems. The red part of the model in the bottom of the slides shows the integration of the higher system architecture model and the lower level of the physical model. So this kind of two characteristics built in one model. The next one, please. So it's the subsystem details behavior. It's the definition graph and the state machine graph to describe the different kind of characteristics of the system. And the right part is generated automatically of the text code. Next one, please. Yeah, so with X language can build the internal data interaction logic of dynamic models. So everything they did actually is to describe all the system characteristics, just as have been done with the traditional methods. These two parts are separated in two models, but for now, the old system elements are built in one model. Next one, please. Now, this is the simulation results. So the simulation results compared with the traditional method is the same. So actually, the traditional method are done by another university experts. So then we cooperate, we borrow the model and do the same thing, but with different method, but get the same result. And the new method can improve the building efficiency. And there are a lot of some new features I just mentioned many times, that we can do a lot of things. We can do the optimization of the whole system with one model and automatically. And actually, it's impossible to do this kind of optimization automatically when you use the traditional way with two models in the two softwares. So now, next one, please. Yes. So in summary, the advantage of MBSE method based on X language, the X language can realize the unified modeling process of system level structure and physical performance. It avoids the conversion from SysMod to Modelic or Simulink or MATLAB. So which may need tedious of work on interface modeling. So this kind of work have to be done manually by human engineers. And X language can easily guarantee the consistency of the system level model and the physical model, which is convenient for backtracking and reflects the system design issues more efficiently and quickly, and hence effectively improve the R&D efficiency of complex products. Next one, please. Now let's come to the conclusions, the future works. So to maximize the value of MBSE, the ability of modeling simulation of physical performance should be integrated into the system level modeling. So we coded, or we prefer to code the MBSE integrated with simulation technologies as modeling the simulation-based system engineering. And to support the idea, the methodology, the philosophy of MSBSE, we developed a new language. We called it X language. So with the language and the corresponding tools, it can embody the philosophy of MSBSE. And fortunately, this language has been approved as a national standard of China and will be published soon, maybe before the end of this year, if everything goes smoothly. The next one. So in summary, the X language adopt a new technical solution instead of the old traditional solution. It can support integrated, it's real integrated, not integration of different softwares or different models. So it's the unified, integrated everything into one models, modeling and the whole system simulation of system architecture and physical characteristics. It can avoid the transformation between the high-level SysML model and the modelic model, so that can ensure the consistency and the global traceability of model description in the whole process of product R&D. And X language have two kind of forms. It's graphics and text. So it can not only realize the graphical modeling without coding, but also if you need code, you can write. Some engineers prefer to write textual code. And in addition, the textual code have a lot of new features. So we can do a lot of things with the text model. For example, the automatically build correlation of models, and the reuse of models is much easier. Use the textual model than use the graphical model. And XLab is the software tools based on X language, and they realize the integration of the simulation with one simulator. So including X language modeling tools, there are graphic conversion tools, compiler, a simulation engine, and also support FMI specification. It's used for the integration of other kind of softwares. Next one, please. So with X language, we can realize the unified modeling process. Next one. We can realize the unified syntax description. Next one. Can realize the unified simulator. Next one. Now, it's the whole system of the X language family. There's a language, there's a methodology, and software. So the whole of the technical systems can embody the realized philosophy of MSBSE. Actually, for now, the software developed by our lab is not for not a commercial level software, so it's just a prototype. Next one, please. And we have built an X language working group. It's under the guidance of National Standardization Committee for the integration of industrialization and informalization. So we have built an X language working group. We have now about 22 members from universities, research institutions, and software and companies, and some manufacturing enterprises. And also, we welcome institutions or researchers or universities from all over the world to join the group. Next one, please. Oh, next one, please. Next. Yeah. Now we have a very short, about 2 minutes, a video to give a whole picture of the X language and X lab. So please play. Excuse me.
MBSE enabled integrated modeling and simulation language. X language. Model-based systems engineering MBSE is the key and inevitable choice to carry out complex system forward design and original innovation, and this is especially true for the development of complex equipment. However, existing MBSE languages, methodologies, and software tools have inherent flaws that lack of capability for whole process collaborative design and simulation, making it difficult to ensure the consistency between various parts of a system and the traceability of the modeling and simulation processes. The X language, together with the corresponding methodology and software, is a new MBSE technology system developed by Beihang University, which integrates a variety of modeling theories and specifications, fundamentally solving the existing MBSE's problem of disconnection between design modeling and simulation validation. The X language provides 2 modeling syntaxes, graph and text, with consistent meta models. On this basis, X language provides a unified formal modeling specification for conceptual design, system architecture, and physical behaviors, and supports hybrid modeling and collaborative simulation of continuous systems, discrete event systems, and intelligent systems, which guarantees seamless integration at all stages of system development, improves the traceability of the whole modeling and simulation processes of the system, and helps R&D teams to achieve comprehensive and efficient information exchange, sharing, and reuse. The X language can be applied to systems engineering and system of systems engineering in a variety of fields, such as aerospace, shipbuilding, automobile, electric power, electronics, communication, and networks. Whether designing complex flight control systems or developing innovative intelligent transportation systems, X language can provide engineers with powerful modeling and simulation tools to support their decision-making and validation throughout the entire process. X language, with its mission of breakthroughs and innovation, brings new experiences and more possibilities to system engineers. Through the university-industry research cooperation, an ever-improving and mature X language technology system will play an active role in improving the efficiency of design and development of complex systems and supporting original innovation.
That's the end of the presentation. I'm sorry because the throat problem and the speech is not very smooth.
Thank you very much, Professor Zhang. It's really comprehensive keynote presentation. You covered quite a lot of materials and need us some time to digest those materials. So in your talk, you mentioned traditional system engineering and also introduced the basics of model-based system engineering compared with modeling and simulation-based system engineering. You actually introduced your own language for modeling and simulation called X language. So this is a very logical and systematic way to make a presentation. We encourage the online audience to send in your questions if you have any. And now I can ask first the question. You mentioned this model-based system engineering. Normally, the model needs to be standardized. And in the modeling and simulation-based system engineering, does it require all the models to be standardized? Or
Yes.
if that's the case, how about the situation if there's new processes, new methodologies being developed that hasn't been standardized? How do you want to handle the situation and use your X language when it's not standardized? Can you elaborate it a little bit?
Yes, the standardization of the models is required by the system engineering. So the reason we call it MSBSE is a modeling simulation. It's just to focus on it, emphasize the importance of simulation. But the standardization process of the modeling actually is the same requirement. But with X language, the process and the result is different. So with the traditional method, actually it's not totally or completely standardized. It's the high-level system architecture can model with one language, and the lower level, the dynamic characteristics of the system will be modeled in another kind of language. So they are not the same language. So if you want to do the simulation, you have to translate or transform one model to another model, put the high-level model into the simulation model, and then you can do the simulation. So the X language, the purpose is to get the total or completely standardization of the whole system with one model. So it will be improvement of the traditional way to do it with two kind of models or two kind of software tools.
Okay. Yeah, thank you. Now we have one question. The question is, thank you very much for the great presentation, Professor. The X language seems promising for MBSE. I have one question. Intelligent agents and reinforcement learning mechanism are employed in the X language to support the modeling of intelligent behaviors. Apart from this, how does the X language support integration with the AI algorithm, like the data-driven ones? Is there some specific APIs?
Yes, it's actually we design a port in the X language syntax to then the compiler and the simulation engine can use the Python algorithms. If you compile to do the programming with the Python programs, the AI algorithms, so the X language engine and the simulator can use it as something like a function to do the whole simulation with other X language models. So this the integration of the AI algorithms can has been designed in the X language syntax. Thank you. It's a very good question.
I'm also waiting for other colleagues from online. If you have any questions, please use this opportunity to discuss with Professor Zhang.
Yeah, actually, the work we are doing is very challenging because it's not easy for engineers or for the industry or to accept a new method that is different from the traditional one, because traditional language and the traditional softwares, there's a lot of commercial tools.
That's
A
true.
lot of companies have developed for many years. If you ask them to use use a new tools or to instead of the old one, it's not easy thing. Especially for some manufacturing enterprises. If you do the MBSV for a lot of years, you have built a lot of models with SysML, so it's not also easy to destroy the old models and use the new one. But fortunately, in China, the MBSE is just a start. So many enterprises haven't started or are going to start. So it's for the new technology. I think there's more chances. So we are still working with some enterprises in China to want to give an example.
Yeah.
A
Now,
demonstration.
actually, there's another question came in. Could you please share some more examples or relevant materials that X language is being used in the smart manufacturing domain, if you may?
Actually, I have so we have a website about X language. I can give the link, but I don't know how to write the link to. So the website is both Chinese and English.
Yeah,
And
it will be difficult for the online audience to see the chat box here. Perhaps the interested audience can contact Professor Zhang directly.
yeah,
so
you can
they
send
have more
email to me
information.
and I can give more materials.
You could also add it to the chat in here, and I will put it on the neural network.
Yeah, that's an additional approach. If you can write it down to the chat box here, and it will be posted online to the online audience in another channel.
Why?
So while Professor Zhang is preparing for writing this additional information, you can also send in your additional questions, if any, from the online audience. So the additional information will be posted to the online audience shortly. If there's
where is the box I can write?
Okay, at the bottom of the screen, you should have a chat box there you can use.
Oh, chat.
Yeah.
I found the chat. Okay. Yeah.
Well, perhaps I can use this opportunity to introduce the next webinar while we are waiting for the additional information. The next AI for Manufacturing webinar is scheduled on December 11th at 10 a.m. Central European Time. Professor Joseph Wanza of Staki in Budapest, Hungary, will present another keynote on breakthrough points for AI in manufacturing. So if you are interested, please join that webinar on December 11th.
Just to be clear, I've put up the website onto the neural network. Thank you, Professor Zhang.
Thank you.
Okay. So if there's no further question, I would like to wrap up today's webinar. I would like to thank Professor Lin Zhang again for delivering a wonderful keynote talk today. And I wanted to thank you everyone, the online audience, for listening and for participating in the discussion. Please stay tuned, have a great day, and bye for now. Thank you.
Thank you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Mm-hmm.